Welcome back to Honors Calculus. In this video, as the title says above me, we're going to be looking at vertical asymptotes. Once again, you're familiar from previous math courses with the idea of an asymptote. A vertical asymptote most often comes up in rational functions and their graphs, also in some trigonometric functions. The classic example is the 1 over x function, which has a graph that looks like this. And we have the tails as the values of x come towards 0 in this direction. That was a very bad try of doing that, but they go closer and closer to the vertical axis. And as you come in from the other side, it slides down, getting closer and closer to the vertical axis as it goes, but never crossing the axis and never turning around and going back the other way. That's what we're talking about when we talk about an asymptote. And so, as with everything else we've done, our goal here is to look at how this is going to work, and try to find a nice tool for putting a theoretical footing on the existence of an asymptote. So if I get my head out of the way, we know that for y equals 1 over x, a vertical asymptote exists at x equals 0. We also know, or if you don't know offhand, you can try graphing a function like y equals 2x plus 2 over x plus 1. And you will find for this particular curve, it's actually a horizontal line. There is no asymptote, even though this is a rational function which is undefined when x equals -1. So that difference is going to be the place that we are worried about. And in order to make sense of that difference, I have a nice theorem on limits. And yes, we're going to prove this using the epsilon delta definition of a limit. No, it's not going to be that bad compared to some of the epsilon delta definitions we've looked at. Let's consider two functions f and g such that f of x is equal to g of x at every point in some interval ab, except possibly at a point called c in that interval. Then the limit as x approaches c of f of x and g of x must be equal to each other if they exist. So it's possible that both functions have a limit which does not exist, but if one has a limit which does exist, then the other one must have the exact same limit. And for the proof of this theorem, I'm actually getting ahead of myself. It's an analysis proof. I want to start with epsilon bigger than 0, but that's actually not the first line. Let's assume that the limit as x approaches c of f of x exists, and we're going to prove that it's equal to the limit as x approaches c of g of x. And I'm still not paying attention to my notes because just existing is not good enough. I need that to be equal to some value called L. Now I can let epsilon be bigger than 0. And definition of a limit says there must be a delta bigger than 0 such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than x minus c is less than delta. And I want to pick my value of delta so that every x which satisfies 0 less than x minus c less than delta is in the interval from a to b. As I've done a couple of times, if there's a bigger value of delta that works for the limit, I can choose something smaller so that everything falls in the interval as well. Another way of saying that is that we have to pick delta so that delta is less than c minus a and delta is less than b minus c. All right, the distance from c to either end of the interval is smaller. But because of that, whenever 0 is less than the absolute value of x minus c is less than delta, it must be that f of x is equal to g of x, right? Except possibly at c, but again, that's why the 0 less than over here is a thing. And so by substitution, we can replace f of x with g of x, and we get that the absolute value of g of x minus L is less than epsilon, which is the definition of the limit of g of x is equal to L. Right? How do we use that? Well, if we want to take the limit as x approaches -1 of 2x plus 2 over x plus 1, and we try just evaluate, right? If we try just evaluating, plug in x equals -1, we get 0 divided by 0. We call 0 divided by 0 indeterminate form. Right? 0 divided by 0 is the only divided by 0 which is not called undefined. It's called indeterminate because we might be able to do something else with it. And to do something else is to find a function which has the same value as 2x plus 2 over x plus 1, except possibly when x is -1. In this particular case, notice that there's a common factor of 2 that you can take out of the numerator. And now there's an x plus 1 in the numerator and then the denominator, which can cancel each other out. Right? You have to be careful because this is not true when x is equal to -1, because that gives you the divide by 0 error and you get no defined value for the function. But because we are looking at the limit, we're looking at everything except x equals -1, and everywhere else you can do this without any trouble whatsoever, and you get 2. So the limit of this function as x approaches -1 is 2. I guess I skipped a step here, sorry about that. This will be the limit as x approaches -1 of 2, which is equal to 2. Right. So you can reduce a fraction And if you can reduce the fraction and get it so that instead of being an indeterminate form, you get a defined value, then the limit exists and it has that value. This is also true when things get a little bit messier, right? The limit as x approaches 3 of x squared plus x minus 6 over x squared minus 9. If you try evaluating this, you get 9. Wait, something went wrong here. I wrote this down wrong. That's why something went wrong. That shouldn't be a plus, that should be a minus. 9 minus 3 minus 6 over 9 minus 9, which is in fact 0 over 0, the indeterminate form we were just talking about. And so there should be some way to reduce the fraction. Whenever you get indeterminate form, you can reduce the fraction. So this should be equal to the limit as x approaches 3. Let's see, factoring the numerator, that's going to be x minus 3 times x plus 2. Factoring the denominator, it's going to be x plus 3 times x minus 3. The x minus 3's cancel each other out, so we're looking at the limit as x goes to 3 of x plus 2 over x plus 3, and that we can just evaluate. You get 5/6. It's very likely that in a college algebra course or pre-calculus or whatever it happened to be called wherever you took it, that you've seen this kind of manipulation to simplify a rational function and get rid of a discontinuity, remove a discontinuity. And that is definitely something that we're going to be looking at more closely throughout the course. But I wanted to go through these examples kind of as a warm-up of how we're talking about this, because the real goal is to look at some problems that you wouldn't have done this with in an algebra course because it gets a little bit messier. So one more example here. Let's take a look at the limit as x approaches 4 of x minus 4 over 6 minus 3 times the square root of x. And if you try evaluating, you get 4 minus 4 over 6 minus 3 times the square root of 4. 4 minus 4 is 0. Square root of 4 is 2. 3 times 2 is 6. 6 minus 6 is 0. So we are looking at an indeterminate form. But this doesn't have the nice effect that we had previously of being able to factor and reduce. We need to look for some other sort of a tool. Thankfully, there is another sort of a tool. Whenever you're looking at a fraction that has a square root in it, one of the things that you're always taught to look at is, can you rationalize? In dealing with limits, you can rationalize denominators. Sometimes you will also rationalize numerators. Whatever has the square root in it, it might help. Not guaranteed, but it might. All right, so to rationalize, we take numerator and denominator, and we multiply by the conjugate of the thing that has the radical. So we'll have x minus 4 times 6 plus 3 root x divided by 6 minus 3 root x times 6 plus 3 root x. I'm going to leave the numerator factored, right? Our goal is to cancel out that x minus 4 so that this thing stops being 0 divided by 0. So there's our 0 in the numerator, and we hope to get rid of it. Right? There is no reason to multiply out an expression if your goal is to factor later on anyway. Think about what you're doing. Don't just blindly work. In the denominator, we can multiply out. 6 times 6 is 36. And then we'll have plus 18 root x minus 18 root x, which are going to cancel each other out. That's why we're taking this route. And then we'll have minus 9 times root x squared, which is x. And I'm not paying enough attention because I'm trying to write and talk at the same time, which is never a good idea. We're still looking at the limit as x approaches 4. I am going across the page instead of just down the page to try to fit more of this problem onto the screen at once, which also makes things a little bit more difficult for me. But now I have that denominator. I notice that there's a common factor of 9, and when I factor out that 9, actually let's factor out a negative 9. When I factor out that negative 9, I get negative 4 plus x, which is exactly the same thing as x minus 4, just written backwards. So we can cancel those out. And we have the limit as x approaches 4 of the negative of 6 plus 3 root x all over 9. And here, finally, we can just evaluate that. We have 6 plus 3 times the square root of 4 all over 9. Square root of 4 is 2. 3 times 2 is 6. 6 plus 6 is 12. And 12 over 9 reduces to 4/3. So we can take the limit of this thing as well. Right. I'm going to label this as a theorem, but I'm not going to prove it. Now that we have seen how to avoid the problem, sometimes the problem cannot be avoided. If the limit as x approaches c of f of x turns into an a over 0 when you try to evaluate, where a is not itself 0, then the graph y equals f of x has a vertical asymptote at x equals c. And that is just a thing that can and will happen. So for example, if I'm taking the limit as x approaches 2 of x squared, x squared minus 4 over x squared minus 4x plus 4, you can see if you try to evaluate when x is 2, you'll get in the numerator 2 squared, which is 4. 4 minus 4 is 0. In the denominator, we get 2 squared is 4. 4 times 2 is 8. 4 minus 8 plus 4 is 0. But in this case, if we factor, sure, we get some x minus 2's to cancel each other out, but that still leaves us with the limit as x approaches 2 of x plus 2 over x minus 2, which in this case is 4 over 0, which is undefined. So with that result, we can claim that the limit as x approaches 2 of x squared minus 4 over x squared minus 4x plus 4 does not exist, and y equals that fraction has a vertical asymptote at x equals 2. Next time, we're going to look a little bit more closely at the limit does not exist case. But for right now, I'm going to wrap up with that. Let's look at some rational functions and their limits, see when they do and do not exist, and we'll take a closer look at describing the situation where the limit does not exist next time. But for right now, let me get my head back out of the way, and here's one for you to take a look at. How about the limit as x approaches 1 of x minus the square root of x all over x minus 1. All right, see what you can do with this problem, and I'll see you in the next video.